The clay drainage tiles were stacked in Anders Lindstrom's barn like a puzzle that made no sense to anyone who saw them. 48 sections of terracotta pipe, each one 3 feet long and 8 inches in diameter. They'd been hauled from the drainage tile factory in Red Wing, Minnesota, at considerable expense. Anders had spent 2 months' wages on them, and now, according to every person who'd seen his plans, he was going to use them to build a heater that would almost certainly explode and burn down his house. It was October 1894, and the Swedish immigrant had been explaining his idea to skeptical neighbors for weeks. He was going to run the clay pipes through his cabin walls in a continuous serpentine path. He'd fire a small combustion chamber at one end. The hot gases would travel through the entire length of pipe, 48 sections connected end to end, 144 feet of clay pipe total, before finally exiting through a chimney. The heat from the hot gases would warm the clay. The clay would radiate that warmth into his home. It was, he insisted, a principle as old as Rome. The hypocaust heating system used by the ancient Romans worked on the same concept. Hot air traveling through channels under floors and inside walls. The masonry absorbing and radiating heat. Efficient, comfortable, and safe. His neighbors thought he'd lost his mind. Martin Olson, whose homestead was closest to Anders, made his opinion clear. Clay pipes aren't meant for fire, Anders. They're meant for drainage, water, not fire. You heat them up, they'll crack. Or worse, they'll explode. You'll have pieces of burning clay flying through your house. It's dangerous. It's foolish. Just build a regular stove like everyone else. Anders was patient in his response, though he'd given it many times. Clay can handle heat. That's why they make firebricks from clay. These pipes are thick, good quality. They're made to handle pressure from earth and water. They can handle heat. But the fire will be inside them, Martin argued. That's different from earth pressure. Heat expands things. Clay is brittle. It'll crack. I've seen clay pots crack in a fire. This is the same thing, just bigger. And when one of those pipes cracks with fire inside it, your whole house goes up. Others shared Martin's concerns. The idea of running fire through clay pipes seemed fundamentally unsafe. Everyone knew clay could crack from thermal shock. Everyone had seen pottery break when heated unevenly or cooled too quickly. The mental image of superheated gases rushing through fragile clay tubes was terrifying. One crack, one failure, and Anders would have an inferno inside his walls. The mockery was constant but not mean-spirited. People genuinely worried for Anders. He was a bachelor, 38 years old, living alone on his claim. If his experimental heater went wrong, he might not be able to escape. He might burn to death trying to prove a point that wasn't worth proving. The local newspaper, the Goodhue County Republican, even ran a small article about Anders's project in late October. The tone was amused and patronizing. "Local Swede plans Roman heating system," the headline read. The article described his plan as ambitious if impractical and quoted several residents who predicted disaster. Anders saved the article. He figured he'd frame it later, after the heater worked, because he knew it would work. He'd seen similar systems in Sweden, not with drainage tiles but with ceramic flue pipes. He understood the principle. He'd done the calculations. The clay pipes could handle the temperatures he'd be generating. The key was to heat them gradually and evenly, preventing thermal shock, and to ensure the combustion chamber was properly designed to create complete burning so no unburned gases would build up inside the pipes. It was engineering, not magic. It was applied physics, not foolish hope. The construction began in early September 1894 and took 6 weeks. Anders started by building a small, highly insulated combustion chamber at one end of his cabin, in the northwest corner. The chamber was made of firebrick, with a cast iron door and adjustable air vents. It measured only 18 inches wide, 20 inches deep, and 24 inches tall. Small, but designed for intense, efficient burning. From the top of the combustion chamber, a clay pipe section angled upward at about 15 degrees. It ran horizontally along the north wall, about 2 feet off the floor, supported by iron brackets Anders had forged himself. At the east corner, the pipe turned and ran along the east wall. At the southeast corner, it turned again and ran along the south wall. This serpentine path continued, with the pipes running in horizontal rows stacked vertically. First row near the floor, second row 3 feet higher, third row near the ceiling. Each turn connected with specially cut pipe sections that Anders had modified to create elbow joints. The joints were sealed with a refractory mortar that Anders mixed himself. Clay, sand, and a small amount of Portland cement. The mixture had to be plastic enough to seal gaps, but strong enough to withstand heat and thermal expansion. Anders tested multiple formulas on scrap pieces before settling on the final recipe. By the time the installation was complete, 144 feet of clay pipe snaked through Anders's cabin, covering 3 walls in a grid of terracotta tubes. The south wall, which had the door and windows, was left open, but the north, east, and west walls were effectively lined with a maze of heated pipes. The final connection was to the chimney, a standard brick structure that Anders had built tall enough to create good draft. The system was ready. Or it would be, once Anders addressed one final concern that everyone kept raising. Thermal expansion. Clay expands when heated. Not much, but measurably. 144 feet of clay. Pipe, if heated from room temperature to 300 degrees Fahrenheit, would expand by about 1.5 inches total. That expansion had to go somewhere. If the pipes were rigidly fixed in place, the expansion would create enormous stress. The pipes would crack or the brackets would fail. Anders solved this with a simple but clever detail. Every 6th bracket was fixed rigidly to the wall. The brackets in between were fixed to the wall but had slotted holes that allowed the pipes to slide slightly. This created expansion joints throughout the system. As the pipes heated and expanded, they could move within the slotted brackets without building up stress. When they cooled and contracted, they returned to their original positions. It was basic engineering, but it required thinking ahead about how the system would behave under operation. On November 5, 1894, Anders was ready for the first test. He'd invited several neighbors to witness, partly to document success and partly to have help nearby if something did go wrong. Martin Olsson was there. So were Jakob Svensson, Peter Andersson, and Henrik Karlsson. 5 men total, standing in Anders' cabin, looking at the maze of clay pipes with expressions ranging from curiosity to dread. "If this goes badly," Martin said, "we're all running. Fast." Anders nodded. "If it goes badly, I'll be running fastest of all. But it won't go badly." He'd prepared his first fire carefully. Small pieces of very dry wood, arranged to allow maximum airflow. He wanted a hot, clean burn, not a smoldering fire that would produce creosote and soot. He lit the kindling. It caught immediately. Within minutes, a good fire was established in the small combustion chamber. Anders adjusted the air vents, tuning the burn. He wanted complete combustion, the fire burning efficiently with minimum smoke. He achieved it quickly. The flames were clear and hot. Very little smoke emerged from the chimney. The hot gases were traveling through the pipe system. The watchers stood tense, waiting for something to happen, for a crack, for an explosion, for disaster. Nothing happened. The fire burned. The pipes began warming up. Anders walked along the pipe runs, carefully touching each section to monitor the temperature. "It's working exactly as designed," he said. "The gases are hottest near the combustion chamber. By the time they reach the chimney, they've given up most of their heat to the clay. Feel this." He gestured to a pipe section near the combustion chamber. Martin cautiously reached out and touched it. It was warm, but not dangerously hot. Warm enough that you wouldn't want to leave your hand there, but not hot enough to burn on brief contact. About 130 degrees, Anders estimated. The gases inside are probably 300 to 400 degrees at this point, but the clay insulates. The outside surface is much cooler. They moved along the pipe run. The temperature decreased gradually as they moved away from the combustion chamber. By the midpoint of the system, the pipes were comfortably warm. By the end, near the chimney connection, they were barely warm at all. "All the heat is being extracted," Anders explained. "By the time the gases exit, they're nearly cool. All that heat is now stored in the clay mass." He let the fire burn for 2 hours, feeding it periodically with small pieces of wood. Not large logs, small splits. The goal was high temperature, not long burn time. After 2 hours, he closed the air vents completely and shut the combustion chamber door. The fire died quickly. Now came the real test. Would the heat stored in the clay pipes be enough to warm the cabin? The answer became apparent within the hour. The cabin temperature, which had been about 55 degrees when they started, began rising. 60 degrees, 65 degrees, 70 degrees. The clay pipes, now acting as a massive radiator, were releasing their stored heat. By evening, 6 hours after the fire had gone out, the cabin was still at a comfortable 68 degrees. The pipes were still warm to the touch. The system was working exactly as Anders had predicted. The neighbors were astounded. They'd expected failure, or at best marginal success. Instead, they were watching a heating system that appeared to be highly efficient and completely safe. No cracks, no explosions, no disaster. Just steady, even warmth radiating from the clay pipe network. "I don't understand," Martin admitted. "How is this possible? The pipes should have cracked." Anders smiled. "Clay is stronger than people think. These pipes are thick, and I heated them slowly, evenly. No thermal shock. The expansion joints let them expand without stress. It's not complicated, it's just careful engineering." Over the next week, Anders refined his firing routine. He learned that one 2-hour fire in the morning and another in the evening kept the cabin comfortably warm even when outside temperatures dropped below freezing. He learned the optimal wood size and burning technique. He learned how to adjust the air vents to achieve the cleanest, hottest burn. And he confirmed that the clay pipes were not just surviving, but thriving. No cracks, no leaks, no problems. The system was remarkably robust. By late November, word had spread beyond the immediate neighborhood. People came from miles away to see the clay pipe heater. Some were interested in building their own, others just wanted to witness the novelty. The Swedish immigrant who'd built a Roman heating system with drainage tiles. It was a story worth seeing. Then December brought the first real test. A cold snap settled over Minnesota in early December 1894. Temperatures dropped below zero and stayed there. On December 9th, the temperature reached -15 degrees Fahrenheit. On December 10th, -20. People huddled by their stoves, burning wood constantly. And Anders's clay pipe heater continued performing, flawlessly. 2 fires per day. The cabin stayed at 65 to 70 degrees. No problems, but the real test was still coming. On December 12th, 1894, a blizzard moved into Minnesota. It would become one of the most severe winter storms in state history. The snow started falling in the afternoon, heavy and wind-driven. By evening, visibility was zero. The wind howled at 50 miles per hour, and the temperature plummeted, -25 degrees, -30, -35. The storm continued through the night and into the next day. December 13th, still snowing, still blowing, still -30 or colder. December 14th, the storm showed no signs of breaking. This was not a normal blizzard. This was a sustained, deep freeze with continuous snow and relentless wind. People across Minnesota were in crisis. Standard heating systems struggled to keep up. Wood stoves and fireplaces had to be fed constantly. Families burned furniture when firewood ran low. Livestock froze in barns. Buildings suffered damage from the extreme cold and snow load. It was a disaster, and it lasted 12 days. From December 12th through December 23rd, the temperature never rose above zero. The snow fell almost continuously. The wind never stopped. It was the longest sustained cold spell Minnesota had experienced since record-keeping began. Anders Lindstrom's clay pipe heater ran continuously throughout the entire 12-day blizzard. He fired it 3 times per day during the worst cold. Morning, mid-afternoon, and evening. Each firing lasted about 90 minutes to 2 hours. Total burn time per day, 5 to 6 hours. The rest of the time, 22 to 19 hours per day, the clay pipes radiated stored heat. The cabin temperature never dropped below 60 degrees. Even at the coldest point, when outside temperatures hit -40 degrees, Anders's cabin stayed comfortable. The clay pipe network, with its massive thermal mass, absorbed heat during the firing periods and released it slowly during the non-firing periods. It was like a battery, charged 3 times a day and slowly discharged in between. The wood consumption was remarkably low. Anders estimated he was using about 1/3 of a cord of wood per day during the extreme cold. His neighbors were burning 1 to 2 cords per day and still struggling to stay warm. The efficiency difference was enormous. But the most impressive aspect was the safety. People had predicted the clay pipes would crack under thermal stress, especially during rapid heating and cooling cycles. They had predicted that the expansion and contraction from repeated firing would cause joint failures. They had predicted disaster. None of it happened. The pipes remained intact. The joints remained sealed. The system operated flawlessly for 12 days of continuous use in the most extreme conditions imaginable. When the storm finally broke on December 24th and the temperature rose to a balmy 5 degrees above zero, Anders's clay pipe heater had proven itself beyond any doubt. It had heated his home through the worst blizzard in Minnesota history. It had done so safely, efficiently, and reliably. And it had used a fraction of the firewood that conventional systems required. If you're realizing that sometimes the craziest sounding ideas are actually the most brilliant, and you want to see more stories about forgotten innovations that still work today, hit that subscribe button. We're uncovering the practical genius of the past, one story at a time. Now let's continue with what happened after Anders's 12-day test and how this changed minds across Minnesota. Martin Olson was the first neighbor to apologize. He showed up at Anders's cabin on December 26th, 2 days after the storm broke. "I was wrong," he said simply. "I told everyone your heater would explode. I was convinced it was dangerous. I was wrong about everything." Anders appreciated the apology but didn't gloat. "You weren't wrong to be cautious. The idea seems dangerous if you don't understand the engineering. But now you've seen it work. Now you know." "I want to build one," Martin said, "next summer." "Will you help me?" Anders agreed immediately. "Of course, and I'll help anyone else who's interested." The interest was substantial. By January 1895, Anders had received inquiries from over 20 families in Goodhue County who wanted to know more about the clay pipe heating system. Some wanted to build their own. Others wanted to hire Anders to design and install systems for them. Anders was happy to share his knowledge freely, but he recognized that building these systems required skills most homesteaders didn't have. Understanding of combustion, knowledge of materials, ability to calculate heat transfer and thermal mass, basic engineering principles. He began offering a weekend workshop in February 1895, teaching the principles of clay pipe heating to anyone interested. 15 men attended the first session. Anders explained the physics. Hot gases travel through pipes, giving up heat to the pipe walls. The pipes, with their thermal mass, store that heat and release it slowly through radiation. The longer the pipe path, the more heat extraction. The greater the clay mass, the more heat storage. It was simple in principle, but the details mattered. The combustion chamber had to be designed for complete burning. The pipes had to be properly supported with expansion joints. The joints had to be sealed with refractory mortar that could handle thermal cycling. The system had to be designed to create adequate draft without allowing too much airflow, which would carry heat up the chimney instead of into the pipes. Anders walked them through every aspect. He showed them his combustion chamber design. He demonstrated how to cut and modify clay pipes to create elbow joints. He explained his mortar recipe. He discussed the mathematics of heat capacity and thermal mass. The attendees took notes. They asked questions. They understood that this was real knowledge, not folk wisdom or guesswork. This was engineering applied to an old principle. By summer 1895, construction of clay pipe heaters began throughout the county. Anders personally helped design and install systems in 7 homes. Others built their own based on his workshops and written instructions he'd prepared. The designs varied. Some were smaller than Anders' system, with only 70 to 80 feet of pipe. Others were larger, with over 200 feet of pipe running through multiple rooms. Some incorporated the pipes into interior walls, creating heat transfer between rooms. Others, like Anders' original design, ran the pipes along exterior walls to maximize heat radiation into the living space. All of them worked. The efficiency gains were consistent. Families using clay pipe heaters reported fuel savings of 50 to 75% compared to conventional wood stoves. The comfort level was higher. The safety record was perfect. Not a single failure, crack, or fire resulted from any of the systems built following Anders' design principles. The local newspaper that had mocked Anders in October ran a follow-up article in March 1895. Swedish immigrants' heating system proves successful, the headline read. The article detailed the 12-day blizzard performance and quoted several families who'd adopted the technology. The tone was respectful, even admiring. Anders kept that article too. The 2 newspapers' articles, framed side by side, told the story of how skepticism turned to acceptance. The clay pipe heating system also attracted attention from outside the immediate area. An article in the Minneapolis Tribune in April 1895 described Anders' system and its performance. The article was picked up by other papers across the Midwest. By summer 1895, Anders was receiving letters from people in Wisconsin, Iowa, North Dakota, and South Dakota asking for information. He responded to every letter, enclosing a detailed write-up of the design principles and construction methods. He never charged for this information. He viewed it as a contribution to the community, a way to help people heat their homes more efficiently and economically. Some heating engineers and stove manufacturers were skeptical. They argued that conventional cast-iron stoves were proven technology. They questioned whether clay pipes could really be as durable as Anders claimed. They suggested that the efficiency gains were exaggerated or that Anders had been lucky with his pipe quality. But none of them could argue with the results. Dozens of clay pipe heaters had been built and operated successfully. All of them showed significant fuel savings. None of them had failed. The evidence was overwhelming. By 1896, the clay pipe heater design had been refined and standardized. Anders had developed a set of design guidelines that allowed people to calculate the appropriate amount of clay pipe for their home size, climate, and heating needs. He'd identified the best sources for quality drainage tiles. He'd refined the combustion chamber design to maximize efficiency, and he'd developed installation methods that ensured proper support and thermal expansion accommodation. The systems being built in 1896 were better than his original prototype, though they followed the same fundamental principles. The science behind why clay pipe heaters work so well involves several factors. First, the thermal mass. Clay has a specific heat capacity of about 0.2 BTU per pound per degree Fahrenheit. A 3-foot section of 8-inch diameter clay pipe weighs approximately 35 pounds. 48 sections, the number in Anders' original system, weigh about 1,680 pounds, or about 4/5 of a ton, heating that mass by 200 degrees. Fahrenheit requires storing about 67,000 BTUs. That's roughly equivalent to burning 4 pounds of dry wood. That stored heat is then released slowly over 12 to 24 hours, depending on firing frequency. The long thermal release period creates steady, comfortable heating without the temperature swings associated with conventional stoves. Second, the heat extraction efficiency. The 144-foot path through the clay pipes gives the hot combustion gases extensive contact with the pipe walls. Heat transfers from the hot gases to the clay through conduction and convection. By the time the gases reach the chimney, they've given up most of their heat. A well-designed clay pipe heater can extract 75 to 85% of the heat from the combustion gases. Compare this to a conventional fireplace, which extracts maybe 10 to 20%, or even a good cast iron stove, which extracts 50 to 60%, and the efficiency advantage is clear. Third, the radiation pattern. The clay pipes, distributed along the walls in a grid pattern, radiate heat from a large surface area. This creates even heating throughout the space. There are no hot spots near the heater and cold spots far away. The entire room receives radiant warmth from multiple directions. This is more comfortable than convective heating from a single point source. Fourth, the combustion quality. The small, insulated combustion chamber allows for very hot, complete burning. When wood burns at high temperatures with adequate air supply, nearly all of the volatile compounds are combusted. Very little smoke is produced. The ash residue is minimal. This complete combustion extracts maximum energy from the wood and produces minimum emissions. The combination of these factors creates a heating system that is highly efficient, comfortable, safe, and economical. The materials cost in 1895 was about $25 for the clay pipes, firebrick, mortar, and hardware. The labor to install was substantial, perhaps 40 to 60 hours, but once built, the system required minimal maintenance and delivered decades of reliable service. The durability of clay pipe heaters exceeded even Anders's expectations. The system in his cabin operated continuously from 1894 to 1921, a period of 27 years with no major repairs. He cleaned the pipes annually by burning a very hot fire to consume any creosote buildup, and he repointed a few joints that had developed minor cracks, but otherwise the system required no maintenance. Other systems showed similar longevity. The clay pipes, when properly installed and gradually heated to avoid thermal shock, proved remarkably durable. The thickness of the pipe walls, typically 1 inch, provided enough thermal mass to moderate temperature changes and prevent rapid heating or cooling that could cause cracking. The expansion joints prevented stress accumulation. The refractory mortar flexed slightly with thermal cycling, maintaining seals without cracking. Several of the systems built in 1895 were still operating in the 1940s and 50s. The technology had proven itself not just effective but enduring. The comparison to other heating technologies of the period is instructive. A standard cast iron wood stove in 1895 cost $15 to $30, comparable to the materials cost of a clay pipe heater. But the stove had to be replaced every 10 to 15 years, as the iron rusted and cracked from repeated heating cycles. The clay pipe heater lasted decades. The stove required constant tending. The clay pipe heater required firing only 2 or 3 times per day. The stove created hot and cold zones. The clay pipe heater provided even warmth. The stove was relatively efficient for its time, maybe 50 to 60%. The clay pipe heater was 75 to 85% efficient. On every metric except initial labor to install, the clay pipe heater was superior. Yet it never achieved widespread adoption outside of a few communities in Minnesota and Wisconsin where Anders' influence was direct. Why not? Several factors limited spread. First, the knowledge barrier. Building a clay pipe heater required understanding principles that most people didn't know. Without direct instruction from someone like Anders, it was difficult to get the details right. Second, the labor requirement. 60 hours of skilled labor to install a heating system was a significant investment. Many homesteaders couldn't spare that time or didn't have the skills. Third, the availability of alternatives. By the early 1900s, coal was becoming more available and affordable in many areas. Coal stoves and furnaces provided convenient heating without the need for custom installation. Fourth, the transition to central heating. By the 1920s, furnaces with ductwork were becoming standard in new construction. The clay pipe heater was a retrofit technology for existing homes, not a solution for new builds. So the technology remained a regional phenomenon. widely used in a few communities where it had been introduced successfully, virtually unknown elsewhere. But for the families who used clay pipe heaters, the benefits were undeniable. Lower heating costs, more comfortable homes, reliable performance in extreme cold. Anders Lindstrom lived in his cabin until 1932, when he sold the property and moved to Red Wing to live with his nephew's family. He was 76 years old. He'd heated his home with the clay pipe system for 38 years. The system was still functioning perfectly when he left. The new owners, a young couple with 2 children, were thrilled to have the heating system included. They operated it for another 15 years before finally replacing it with an oil furnace in 1947. When the clay pipes were removed, they were still intact. No cracks, no failures. After 53 years of continuous use, the system was still functional. The pipes were donated to the Goodhue County Historical Society, where several sections remain on display today. Anders died in 1938 at age 82. His obituary in the Red Wing newspaper mentioned his innovative heating system and his generosity in sharing the knowledge with others. Several people who'd learned from Anders continued teaching the technique to younger generations. A few clay pipe heaters were built in the 1950s and 60s by people who remembered the old systems and wanted to recreate them. But by then, the technology was seen as a historical curiosity, not a practical solution. Modern heating was easier. Natural gas, fuel oil, and electricity had made wood heating obsolete for most people. The knowledge was fading. In the 1970s, during the energy crisis, there was brief renewed interest in efficient wood heating. Some researchers studying alternative heating methods rediscovered the clay pipe heater principle. They called it a thermal mass accumulator or heat storage system. They didn't know about Anders Lindstrom or the Minnesota homesteaders who'd built dozens of these systems 80 years earlier. They thought they were innovating. They were actually rediscovering. This pattern of forgetting and rediscovering is common with vernacular technologies. The knowledge exists in specific communities, serves them well, but never gets widely documented or formally taught. When the generation that practiced the technology dies, the knowledge dies with them unless someone makes an effort to preserve it. In recent years, there's been renewed interest in thermal mass heating as part of the broader sustainable building movement. Rocket mass heaters, which use a similar principle of extracting heat from combustion gases and storing it in masonry mass, have become popular in some alternative building communities. These modern systems typically use more sophisticated insulation and combustion chamber designs, but the fundamental concept is the same as Anders's clay pipe heater. Burn a hot, clean fire. Extract the heat into thermal mass. Let the mass radiate the heat slowly. The efficiency and comfort benefits are identical. Some modern builders have even recreated clay pipe heaters specifically, using either ceramic flue pipes or, in a few cases, actual clay drainage tiles like Anders used. The results confirm what Anders knew in 1894. The system works. It's efficient, it's safe, and it's remarkably durable. The concerns that Anders's neighbors raised about the clay pipes exploding or cracking were based on incomplete understanding of materials and thermal stress. Clay can indeed crack from thermal shock if heated or cooled too rapidly or unevenly. But with gradual heating, proper support, and expansion accommodation, clay pipes can handle repeated thermal cycling for decades. The key is engineering, understanding how materials behave under stress, and designing systems that work with those properties rather than against them. Modern materials science can explain exactly why Anders's design worked. Clay has relatively low thermal conductivity, about 0.2 to 0.4 watts per meter Kelvin. This means it heats slowly and cools slowly. The thick pipe walls, about 1 inch, provide enough thermal mass that the interior and exterior surfaces heat at nearly the same rate, preventing the internal stresses that cause cracking. The refractory mortar used for the joints has similar thermal expansion properties to the clay pipes, so the joints expand and contract with the pipes rather than creating shear stresses. The expansion joints allow the system as a whole to accommodate the linear expansion of the pipes without building up compressive forces. Every detail of Anders's design, whether he understood the formal engineering principles or not, worked to prevent the failures his neighbors had predicted. He'd built a robust system because he'd thought carefully about how it would behave under operation. The 12-day blizzard in December 1894 was the ultimate stress test. Continuous operation for 12 days, with 3 firing cycles per day, in temperatures down to -40 degrees. That's 36 firing cycles, 36 heating and cooling cycles for the clay pipes under the most extreme conditions. Not only did the system survive, it performed flawlessly. No cracks, no leaks, no degradation. After that test, no one could credibly argue that the system was dangerous or fragile. Before we wrap up this story and look at Anders's legacy, I want to ask you something. If these forgotten innovations fascinate you, if you're seeing how much practical knowledge we've lost, then make sure you're subscribed. We're bringing these stories to life week after week. Hit that subscribe button and join us in rediscovering the wisdom of the past. Now let's finish with what Anders's clay pipe heater teaches us about innovation and skepticism. The story of Anders Lindstrom's clay pipe heater is fundamentally about the difference between reasonable caution and uninformed skepticism. His neighbors' concerns were reasonable on the surface. Clay pipes carrying hot gases did seem potentially dangerous to people unfamiliar with materials science and thermal engineering. The worry about cracking and explosion wasn't irrational. It was based on everyday observations of how clay objects sometimes behave. Pottery cracking in fires, bricks spalling from freeze-thaw cycles, these were real phenomena. But the leap from clay can crack to this specific application will fail was based on incomplete analysis. Anders' neighbors didn't understand the difference between thin pottery and thick pipe walls. They didn't understand thermal mass and gradual heating. They didn't understand expansion joints and refractory mortars. Their skepticism wasn't based on engineering knowledge, it was based on fear of the unfamiliar. This is a common pattern when innovative ideas challenge conventional methods. People default to worst-case thinking. They imagine all the ways something could fail. They don't consider whether those failure modes are actually likely given the specific design details. They see surface similarities to things that have failed before and assume this will fail too. Anders's response to the skepticism is instructive. He didn't argue. He didn't try to convince through debate. He simply built his system and demonstrated that it worked. Actions over words, results over rhetoric. When the 12-day blizzard proved his heater's reliability beyond any doubt, the skeptics became converts. Not because Anders had argued them into submission, but because the evidence was undeniable. This approach works when you have confidence in your knowledge and the patience to let results speak for themselves. The broader lesson is about the value of cross-cultural knowledge transfer. Anders brought a heating concept from Sweden and adapted it to Minnesota conditions, using locally available materials. The principle was ancient, Roman hypocaust heating. The implementation was innovative, using clay drainage tiles instead of masonry channels. The result was a heating system superior to anything else available in 1894 Minnesota. How much knowledge exists in other cultures, other traditions, other contexts that could solve problems we face today? How often do we dismiss ideas because they're unfamiliar, because they challenge our assumptions, because they seem strange? Anders's clay pipe heater seemed strange, until it worked. Then it was brilliant. The persistence of vernacular knowledge is another theme. Anders's heating system was never patented. It was never commercialized. It was never formally taught in engineering schools. It spread through personal instruction and community sharing. It existed as practical knowledge within a specific community. And when that community moved on to other heating methods, the knowledge faded, but it never completely disappeared. A few people remembered. A few examples survived. And when conditions changed and people started looking for efficient wood heating again, the knowledge could be rediscovered. This suggests that preservation of vernacular knowledge is important even when that knowledge doesn't seem immediately relevant. We don't know what future conditions will require. We don't know what problems we'll face decades or centuries from now. Maintaining diverse knowledge bases, including traditional and vernacular techniques, provides options when we need them. Anders's clay pipe heater also demonstrates the importance of understanding principles rather than just copying methods. Anders didn't just copy a Swedish design, he understood why it worked. He understood heat transfer, thermal mass, combustion efficiency. That understanding allowed him to adapt the concept using different materials in a different context. If he just tried to copy a specific Swedish design without understanding the principles, he probably would have failed. Understanding why things work is more valuable than knowing that they work. The economic impact of the clay pipe heaters on the families who adopted them was substantial. Reducing firewood consumption by 50 to 75% freed up enormous amounts of time and labor. A family that had been cutting and hauling 8 to 10 cords of wood per winter now needed only 2 to 3 cords. That's weeks of saved labor, time that could be used for other productive activities or simply for rest. The cost savings in terms of labor translated directly into improved quality of life. Less exhaustion, more time with family, more time for education, crafts, or other pursuits. The comfort level was also economically valuable in a less direct way. A warmer, more comfortable home meant better health. Fewer respiratory infections, less stress on the body from constant cold. For children and elderly family members in particular, the consistent warmth could be the difference between health and illness, between thriving and merely surviving. These benefits are difficult to quantify in dollar terms, but they were real and significant. The safety record of the clay pipe heaters is worth emphasizing. Over a period of more than 50 years, with dozens of systems in operation, there were no fires, no injuries, no failures that resulted in property damage or harm to people. This is remarkable, given that these were experimental systems built by homesteaders without formal engineering training. The success rate was 100% because the fundamental design was sound. Clay pipes could handle the application. The engineering principles were valid. The concerns about explosion and fire, while emotionally compelling, were not supported by the physics of the situation. This perfect safety record contrasts sharply with the risks associated with conventional wood stoves of the period. Stove fires were common. Chimneys caught fire. Stoves cracked and leaked carbon monoxide. Burns from touching hot stove surfaces were routine. The clay pipe heater, with its lower surface temperatures and enclosed combustion system, was actually safer than the accepted alternative. But people feared it because it was unfamiliar. They accepted the known risks of stoves because those risks were familiar and understood. The unknown risks of a new technology seemed more dangerous even when they weren't. This is human psychology, not rational risk assessment. Anders Lindstrom's legacy is modest but meaningful. He's not famous. There are no monuments to him. His name appears in a few historical records and newspaper articles, but he's not remembered as a great inventor or innovator. Yet he had a real impact. He brought knowledge from one context to another and adapted it successfully. He shared that knowledge freely, helping dozens of families heat their homes more efficiently. He demonstrated that unconventional approaches could work if they were based on sound principles. And he left behind a technology that, while not widely adopted, proved the value of thermal mass heating and contributed to the broader knowledge base of efficient heating systems. In an age where we celebrate disruptive innovation and transformative technologies, Anders's story reminds us that most progress is incremental and local. It's about taking what works in one place and making it work in another. It's about sharing knowledge within communities. It's about the patient work of building, testing, refining, and teaching. It's not dramatic. It's not flashy. But it's how most real improvement happens. Everyone said his clay pipe heater would explode. They were certain that heating drainage tiles with fire was dangerous and foolish. They predicted disaster. They mocked him for wasting money and time on a system that couldn't possibly work. Then it worked for 12 days straight during the worst blizzard in Minnesota history. Then it kept working for decades. Then it proved that the skeptics were wrong about everything. The clay pipes didn't explode. They didn't crack. They didn't fail. They stored heat and radiated warmth just as Anders had said they would. The ancient principle of thermal mass heating, implemented with modern materials, created a system that outperformed everything else available. Anders Lindstrom was right. The skeptics were wrong. And the lesson is simple. Don't dismiss ideas just because they seem strange. Don't assume failure just because something is unfamiliar. Understand the principles, look at the engineering, test carefully, and be willing to admit when you're wrong. Anders's neighbors did that. They admitted error. They learned from him. They adopted the technology themselves. That's how progress happens. Not through stubbornness and dogma, but through openness and evidence. The clay pipe heater worked. It worked better than anyone expected. And it worked because Anders understood heat, materials, and engineering. Because he was patient enough to let results prove his case. Because he was generous enough to share what he knew. Everyone said it would explode. It didn't. It heated homes for generations. And that's a lesson worth remembering.